This video is going to go through the formal definition of a Turing machine. I'm not going to go over a specific example for time constraints. So the key thing I want you to remember before this video is that all of the machines that we've described so far have been definable using a tuple notation. So the finite state machines were a 5-tuple of states, alphabet, start state, accepting state, and transition function. The pushdown automata was almost the same sort of thing, except the transition function had to be a transition relation, and we also had an extra alphabet of symbols that we could put onto the stack. I also want you to keep a basic idea of the Turing machine as this finite state machines with access to a tape, and that was from the last video. So a Turing machine is just a state machine, as we said, and it has a finite number of states, just like all the machines that we've looked at so far. Instead of having a stack like the pushdown automata has, it has an infinite tape, which extends in either direction. And this tape is made up of cells that can contain one symbol in them. The machine also has access to a head, which sits on one tape square at a time and can examine what is in the state in that square. So if there's an A, that tape head can know that there is an A there. This head, on any transition in between the states, it can help decide which transition to take based on what is currently under the tape head, and it can also modify the value in the square, and it can move to the left or the right by one space. So how do we describe this as a tuple? Well, it turns out we can describe it as a 6-tuple that looks almost exactly like the pushdown automata 6-tuple. Actually, it looks exactly like the pushdown automata 6-tuple, and it is very, very similar. So the first element K represents the states, and it's no different than it has been since we started this course with the finite state machines. It's just a set of states that has finite size. Sigma, as always, is the input alphabet. So it's the alphabet that the strings that our machine, in this case our Turing machine, has to deal with, the strings that the machine has to deal with have to come from this alphabet. But because we have this tape that has spots on it, we're going to have a symbol that represents there being a blank in the cell at the moment. And we're going to represent that using this empty square symbol. So because that has to be able to represent stuff that is outside the realm of the input strings, our input alphabet cannot contain this symbol. So the blank symbol is never an element of sigma. So when we defined our pushdown automata, we had to define a set of symbols which could go on the stack, and this we represented using a capital gamma. Now, for the pushdown automata, the input alphabet and the stack alphabet didn't have to have any relationship. They could be completely distinct. However, when a Turing machine accepts a string as input, that string is written onto the tape. So every element that can appear in an input string must also be able to appear at some point on the tape. So when we define our new extra alphabet, which we call the tape alphabet, and we also represent using a capital gamma, that must contain all of the elements from our input alphabet. We also say that the tape alphabet gamma contains a symbol called the empty symbol. And this is the empty symbol or a blank, but it is the symbol that represents that a cell on the tape does not contain anything in it. And it is important that that is not an element of our input alphabet. So what we end up having is that this statement holds true. Sigma is a strict subset of gamma. Our input alphabet is a strict subset of our tape alphabet. I'm going to leave the transition function delta until the end. So the next element is S, which is our start state, and it's the same as it has been again since we started with the finite state machines. So it is just a single special element of K that the machine always starts in. Finally, up until this point, we've had a subset of the states which have been called the accepting states. So these were states where if we landed in them in a finite state machine and we had an empty string we accepted, and a similar definition for the push-down automata. In this case, we are going to define the Turing machines to be a little bit more general than just accepting and rejecting. So what our set of special states are is the set of halting states. So this is a set of states that if the machine arrives in these states, it halts. So in this case, these are states that there won't be a definition for in delta. So finally, the last bit of our tuple, which is always the most important and most complicated part of the tuple, our transition function. Now with the push-down automata, we just let this be a transition relation, and in theory this could just be a transition relation, but for the moment we're going to define just a transition function. So our Turing machine is going to be a deterministic model. Now what that transition relation says is that given a non-halting state, so that is one of the states from K that isn't a state in which the machine just halts in, and a tape symbol, so that is the symbol that's currently sitting under the head of our tape. Given the pair of those two, it gives us the state that it has to transition into, and in this case it can be halting, and a symbol to write onto the onto the tape, and a direction to move the head. Now for the moment we're going to define that just to be left and right, but we'll see in a moment that defining that as being able to stay still doesn't change the power of the thing, and it just makes it easier for us to program with. But for the moment it can move left and right. So for example, if we have an A sitting here and we are currently in state Q0, and we have and Q0 is not an element of our halting state set, then we may have a transition that looks like Q0 with an A go to something else. So in this case, let's say that it goes to another state Q1 and writes B and it moves right. So what our machine will do is it will be in Q0 at the moment. It's going to see that underneath the tape head it has an A. It's going to replace that A with whatever is over here down the bottom. So in this case it's going to replace that with a B, and it was said that it had to move to the right, so the tape head is going to stop being here and it's going to move over to here. So that's all the elements in delta are. There's just a series of these, and by combining all of these 6 things together we end up with an incredibly powerful formalism that lets us describe almost everything that we can do with a computer at this point. So all I want you to have grasped from this video is what the formal definition of a Turing machine is, and that is as a 6-tuple with states, input alphabet, tape alphabet, start state, halting state set, which is a subset of our states, and a transition function.